So I'll give you a brief introduction, Lawrence, and then you can start. So Lorenz Eberhardt is a theoretical physicist working on string theory and quantum gravity. His research focuses on dualities, meaning unexpected equivalences between different physical descriptions, and on developing methods for exact computations in quantum gravity. His work includes an exact solution of three-dimensional quantum gravity with negative cosmological constant, applications of analytic number theory to string amplitude computations, and a direct proof of the ADS3 CFT2 correspondence. He's an assistant professor at the University of Amsterdam since 2023, and after a long-term postdoctoral postdoc position at the Institute of Advanced Study in Princeton, he earned his PhD at ETH Zurich in 2019. So please take it away, Lawrence.
Thank you very much. Thanks very much for the invitation. It's nice to be with you. And today the plan is just to tell you a little bit how string theory works. As I understand, not everyone in the audience was exposed to these ideas. So it's a talk that I think one could have given maybe 40 years ago, and just explaining the ideas that were around back then. And then next week we're going to have discuss some new developments. Yeah, let's get started. And please feel free, as we said before, to interrupt me at any time, ask questions, and so on. So let's start by trying to recall some of the problems in QFT and how string theory is supposed to solve them or address them. And essentially in QFT, at least for me, there are always two problems. One is that QFT is not UV complete, typically. So if we talk about the standard model or QCD, well, QCD itself is maybe fine, but the standard model, we know that if we go to higher and higher energies, there will be more particles coming in, and eventually we hit some renormalization scale. So from a formal point of view, we always have to apply some renormalization procedure. And at some point, we cannot say anything if we are above the renormalization scale. And the other very famous problem, of course, is that QFT does not incorporate gravity. So if we want some theory that consistently unifies gravity and QFT, or quantum mechanics, then QFT will always break down. Again, essentially because of the same reason that with gravity, this renormalization problem is much, much worse than without gravity. And so that's a bit of a bad situation. And one way to still learn about physics at very high energies is to ask yourself, well, whatever theory you have there, it must be consistent with all the constraints that we learned in physics. So, for example, very basic constraints like causality or consistency with special relativity. Of course, it has to be also consistent with low energy physics, but that turned out to be a very, very hard thing to try to impose the low energy physics constraints on high energy physics. But so let me write this. So this will be sort of the guiding question also for the next talk. And of course, the first order approximation, this is a completely crazy question because the answer is certainly going to be extremely complicated. There will be maybe many new particles. There are many scenarios, and we do not know which one is the right one. And so there are many details that we do not know, and I think we will also not learn very soon. But there are many that you might hope that there are some underlying patterns that are independent of whatever precise phenomenological scenario is realized in nature. So you can ask for any underlying patterns. So just to give you an example, what I have in mind is you can, for example, ask to prepare some gravitational waves. So build some huge collider of the size of the solar system or something. So of course, grant agencies are not a big fan of this, but let's suppose we build such a collider and let's collide two very highly energetic gravitational waves. Then there will be some scattering process happening, and there will be all kinds of objects generated. So there can be particles like we know them, like Higgs bosons or even quarks, whatever, all kind of particles. But you can also imagine generating black holes in this collision and all kinds of more exotic particles. And then you can measure the decay products of your collision. And yeah, so you can ask, of course, you will not know the details of this collision because there will be new particles potentially that are generated. But you can ask, for example, how does the amplitude behave at very high energies? Does it go down? Is it UV soft? Is it UV complete? Or in quantum field theory, it will go up. It eventually explodes because you're hitting the renormalization scale and your theory doesn't make sense anymore. And it will turn out that string theory is actually quite good at answering these kind of questions. Very good. So the perspective I'm going to take is not, again, to try to do some model building, but we'll look at top-down construction. That means you start with some theory that you know is consistent in the UV, and then you see what it predicts for the UV. And you're not trying to connect low energy physics because that typically is very hard, and there are many ways of doing it. And so, of course, that will leave a gap in our understanding, but yeah, we do what we can.
When you say low energy physics, sort of how low is low?
Everything is in a standard model for us is low.
Okay. Okay.
So then how high is high?
How high is high? Essentially, it's as high as you want, so it can be up to the Planck scale. What we will talk about in string theory is up to the string scale, and the string scale is not exactly the same as the Planck scale. That depends. So there's one dimension as constant that essentially you can play around with. And yeah, we do not know the value of this.
Why not aim beyond the Planck scale if you're just...
You can, in principle, also go beyond this Planck scale. Yeah, it's just computationally will be very hard because you will need to control the theory non-perturbatively, and that's very hard.
Okay, I'll come back to that. Yes.
Very good. So currently, the only theory that where you can do this kind of computations is string theory. Oops, sorry, something happened. So of course there are other models around, but they are currently not able to do these kind of computations. So we'll stick with string theory. And string theory, it was invented by particle physicists. It was actually invented for QCD purposes. So what string theory is good at is computing amplitudes. It's really a particle physics theory. So that's originally in the 70s, 80s, what it was developed for. And so the observables we're going to look at are string scattering amplitudes. So these are precisely if you would construct some huge collider and you measure cross sections of various processes, then these are in principle the objects you're measuring. So they will be our probe into UV physics. Okay. Any questions?
Everybody looks happy.
Everyone's happy. So tell me also if I'm going too fast, too slow, the level is too high, or something like that. I can adapt.
Yeah.
So
Just want to check, is this connection with low energy physics that what swampland's all about?
yeah, so Swampland is trying to, let's first go 40 years in the past or 30 years in the past. So there are many attempts to try to, so as you might know, and as I'll discuss, string theory works in 10 dimensions. And obviously we're not living in 10 dimensions, but there are many ways to go from 10 dimensions to 4 dimensions. So the most famous way is to do Calabi-Yau compactification. But already that's a very restrictive scenario, but there are many ways of doing that. And so it's not going to be possible to pick the correct compactification that reproduces our standard model because there are just way too many choices. And also computation is hard. So Swampland is trying to turn around the logic and it's asking, well, okay, we do not know which compactification is correct, but we're trying to find again patterns that extend to all compactifications. So for example, one of the conjectures is that you cannot have that gravity is always the weakest force in these compactifications, regardless what compactification you pick. So if you want, you can say that as a prediction of string theory, that gravity is in a very precise sense always the weakest force in whatever low energy theory you have. And that might or might not impress you because, well, it is satisfied in nature, but to call it a prediction is maybe a bit bold. But
Thank you.
yeah, so but that's the logic of the Swampland program. And then there are many sort of general constraints that we know on low energy physics. But that's a far cry away from saying what is the mass of the electron.
Thank you.
Yep. Very good. Any other questions? Okay, very good.
Shy away from asking, right? No. If you feel like you want.
So now the plan of the rest of the talk is to tell you essentially how string amplitudes work. And for this, we're going to go back first to QFT and remind ourselves a little bit about Feynman diagrams. And especially, I think you have probably seen most of you Feynman diagrams, but perhaps you have, I can offer you a new perspective that not everyone has seen. And in particular, I want to describe quantum field theory in the so-called word line formalism, since that is the one that readily generalizes to string theory. So as we've probably seen, perturbative QFT is described by Feynman diagrams. And Feynman diagrams are basically if you want, a history of what happens in the scattering process. So if, again, you're considering some scattering of particles, and I'm going to read the diagrams from left to right. So there are two particles coming in, and then they're scattering somehow, and they're going out. Then let's say we're in 5⁴ theory, just for simplicity. Then we know that there's a tree-level process, which is just a contact diagram. And then there can be loop-level processes to this to the scattering event. For example, this, and so on. So you're supposed to write down all the diagrams that come to mind. And then there's some vertex factor for every diagram, and you're writing down propagators. And let's make an example. So there are Feynman rules, and if you're computing this diagram, then you're supposed to put some loop momentum k here, and then on the other side I have momentum p1 plus p2 minus k by momentum conservation, and in this diagram in scalar QFT will just be a loop integral of the following form: 1 over k squared There's also an I epsilon prescription, but let me not talk about it at the moment. So I'm just going to view it as a Euclidean integral. But it will just be the product of the two propagators. So there's one propagator over here, and there's one propagator over here, and they will just give you these factors. And let's recall also what sort of all the problems were about in QFT. The problems is that when d is bigger or equal than 4, this integral is going to be divergent because it's scaling like 1 over k to the 4 for a very large momentum k. But then I'm going to do d integrals over k. So when d is bigger or equal than 4, this is not going to converge anymore. And the divergence is coming from the region where k is very large. And large k means large momentum and large energies. So that's a UV divergence. Sometimes diagrams can have also IR divergences, but IR divergences are sort of physical. They're actually part of the theory. And whenever you have an IR divergence, it usually means you're computing some kind of, you're computing some object that is not completely well defined. Okay, so this is the standard formalism of Feynman diagrams. And one nice trick is the following. To do these integrals, you can introduce so-called Schwinger parameter. The Schwinger parameter is just the observation that the propagator, 1 over k squared, you can write it as an integral from 0 to infinity of some auxiliary parameter L for the moment of this integral. So if you do this integral, it will knock you down again 1 over k squared. So that's an easy identity. And we'll discuss the physics of that identity in a moment. But what it helps you is that you can plug this in to whatever Feynman diagram you have. And so for every propagator, you're now going to introduce one of these Schwinger parameters. And the good thing after you did this is that the integral over the loop momentum is Gaussian. So you can do it. In this case, it will give you, I think, a double integral from 0 to infinity. And then you just do the Gaussian integral, and the Gaussian integral will bring you down some power of these lengths, of these Schwinger parameters. And then you remain with some exponential that arises from completing the square of your Gaussian integral. In this case, it gives this integral. The details are not particularly important, but the important thing is that there is this rewriting. And so what is this doing? So you can do that with any diagram. And so instead of integrating over loop momenta, you can also integrate over the Schwinger parameters for every internal propagator. And there's now a very natural way of thinking about this, what this is doing. Well, this integral is precisely coming about by doing an integral over the length, the proper length of these internal propagators. So what you should think of as being L is the proper length of the propagator. So in other words, what you're taking an integral over in this, once you go to the Schwinger parameters, is an integral over all possible metrics on this graph. Because on the graph, you can have metrics that ascribe some length to this line. And the only invariant quantity of this metric, because it's a 1D manifold if you want, with some singularities, is the proper length of the various pieces of the manifold. So you can view this integral over L1 and L2 as an integral over metrics on this graph modulo diffeomorphisms, so modulo just coordinate changes. And the only what we call diffeomorphism invariant quantities. So the only quantities that are independent of the choice of coordinates, the only information in this metric is the length of this line and the length of this line. Everything else is sort of redundant information in the metric. So you can view your Feynman integral as an integral over the space of metrics on this 1D surface, 1D graph. And of course, this graph is not special. This works for any graph. And so what Feynman diagrams are doing they're integrals over metrics on graphs. And another maybe slightly pointed way of phrasing this is to say that Q of t, or perturbative Q of t, is nothing else than summing over all possible 1D manifolds or 1D graphs with certain rules. So you're allowing certain singularities. You're integrating over all the metrics on these 1D manifolds up to diffeomorphisms, so up to coordinate redefinitions. And so what this is 1D quantum gravity, because 1D quantum gravity will precisely be the sum over all 1D manifolds. And you're doing the gravitational path integral of these 1D manifolds. So another way to think about Q of t is to say that it's 1D quantum gravity on the world line. So the world line is your space, your one-dimensional space where quantum gravity happens. Let me box this. So this statement is a bit confusing if you have not seen it, or maybe surprising. So maybe I should ask for questions.
Yeah. Sorry, could you elaborate a bit on how you come to the interpretation of L being a proper length of the propagator?
Yeah. So yeah, I haven't really told you why. So one dumb answer to this question is you make dimension analysis and you see that L has the units of length, and then this is the only length there is. But there's also more. So I've cut many corners here, but the sort of proper way, if you want, of introducing that is you start with a 1D word line, and you're trying to define this 1D quantum gravity. And how are you going to define it? Well, you're going to write down an action for this 1D theory. So I haven't even told you what the action is, right? And I told you the action, this L is the proper length of the word line. So what the action is going to be is just the action that you learn for, in general relativity for the motion of a particle on your geodesic. So the word line action is going to be just an integral over the word line with some coordinate choice, let me call it tau, and then you put the induced metric there. So this is just the action that computes the length of the word line.
Yeah.
So you start with this action, and starting from that, you can rederive your Feynman rules actually. So what you need to do is it's not completely straightforward to quantize this action and do actually quantum mechanics with this because of the square root, but there are various tricks that you can do. And once you define your action, you see, then you have to compute the 1D path integral on all these kind of topologies. So in particular, for every propagator, you will need to compute some functional determinant. So it's a 1D functional determinant of some determinant operator that lives on the line bundle. And what you can see is you can reproduce these, you reproduce, the Feynman rules will be on this side. So they give you these kind of terms. And there are some general rules for, this looks a bit random what is in the exponent, but there's some general rules for any graph, what kind of polynomials and so on you get here. Yeah, and then you can check that after you do this transformation, you go back to the usual Feynman rules.
Okay.
So, but that's a kind of a long story to go through all of these steps. So I just cut these corners.
Yeah. Thank you.
Yeah.
You mentioned that L's has dimensions of length, but it looks like it's length squared, no?
That's right. Sorry. You're right. Sorry, now I'm confused. Good point. Yeah, sorry, I'm a bit confused. You're right. I don't have a good answer at the moment. Yeah.
Okay, no worries.
Related to the square root that you have in your action in a way. I mean, you could possibly also start this in position space and do word line formalism on that side for your propagators and link this up to that. And there you also have something that has the same dimension as the proper, right? Yeah.
Yeah, you want to land on position space Feynman rules in the end, you said.
Yeah, right. If you come from there,
Yeah.
you write down your Feynman path integral in that world in the position space word line formalism.
Yeah.
There your parameter is also it has the same as also a squared length dimension. Then
Yeah.
but then you still have you have a square of a length interpretation. I mean, it's a square of a length.
Yeah.
That one.
Yeah. Yeah.
I don't see how to connect it to this directly, but well, you Fourier transform at some point.
Yeah.
Just to check, this kind of resembles what a melon transforms. Is there any actual relation? Just being
you have in mind of conformal field theories, the Mellin transform, or just the mathematical Mellin transform?
more of around CFTs and doing QFT on like ADS itself.
Yeah, it's maybe somewhat similar. Yeah, I mean, the details are kind of a bit different. So Mellin transform, you go to yeah, I mean it looks a bit similar, but the Mellin transform involves also some gamma functions in there and so on. Yeah.
A lot more simple.
Well, you also get the gamma functions from here immediately if you change your variables a little bit to combine. So.
Okay, thank you.
Very good. So this is if you want a different take on QFT. And once you have that take, it's sort of simple to go to string theory. So let's replace our word lines by so-called worldsheets. So what in string theory I'm sure you heard is what you're doing is you're replacing your particles by strings. So this will be 1D extended object in space. And so that also means that you're replacing your scattering amplitude or your Feynman diagram. So let me draw the same one by some object that is sort of thickened. So you can view this as the history of your particle through spacetime. And now if you replace all the particles in this Feynman diagram by strings, well, the incoming particles will be sort of tubes. So you have the spatial direction, but there's also the time evolution. And then at some point they're going to join. And well, here it's a one loop diagram. So they're going to join, but then split again and then join again. So my artistic skills are maybe not so great, but hopefully it's clear what I'm drawing. So they're joining and then there's a loop and then eventually they're again scattering out to infinity here. And so now for the string, the history through space-time sweeps out not a bunch of lines, but sweeps out a two-dimensional surface. And this two-dimensional surface is called worldsheet. in analogous in an analogy to grid lines. And the important thing that you should already notice is that this one has corners. And so we need some Feynman rules, what happens at the corners, whereas this one is still an interacting diagram, but it has no corners. And the essential reason why there are many QFTs is that you can make up the rules at the corners. So these are all the interaction terms in your Lagrangian, and you can write down Feynman rules. And there are many possibilities for these Feynman rules because you can do phi to the 4 theory, you can add some phi cube term, or you can add more fields, or you can do essentially whatever you want. Whereas in string theory, this is not going to be possible because in string theory, you're talking about these smooth worldsheets, and you cannot make up new rules what happens at the corners because there are no corners. So string theory is very much unique in that there are some small number of discrete choices, but you cannot make up a lot of choices. And now you're just basically trying to replace. So on the QFT side, you're integrating over all metrics on your graph, modular diffeomorphisms. And on the string side, you're just trying to replace this, but now you're going to integrate over all the metrics on a 2D surface. Let me call this sigma, being this 2D surface that is swept out by the string. And of course, you also need to divide by diffeomorphisms. So this sounds like a bit of a daunting thing to do, because if you think about metrics on 2D surfaces, now there are many diffeomorphism invariant quantities, because you can have, let's say, if you start with a sphere, you can put the round metric on the sphere, but you can also put a very potato-shaped metric on the sphere. In particular, the curvature of the sphere is some diffeomorphism invariant quantity. So this is a very infinite dimensional space. So that sounds like it's going to be extremely hard. However, there's a miracle that happens. So let me tell you the miracle. And the miracle is that, well, I haven't really talked very much about the integrand that we're going to integrate. So also for the QFT case, we just derived it by coming from the usual Feynman rules in momentum space and then doing this transform. But in the string case, again, you can try to develop the theory properly, where you have to write down some action for this 2D theory, and then you need to quantize that action. And what happens is that if you write down this action, well, maybe I can write it. Well, if you write down the action, it turns out that it's not, it is invariant under further symmetry. So the action, this is often called the worldsheet action, is invariant. So of course it's invariant under diffeomorphisms. So that just means that it's independent of coordinate choices, but it's also invariant under taking the metric on the worldsheet and rescaling the metric by some function. So phi is any function. Such a transformation is called Weyl symmetry. So this sounds like a bit of a technical point, but it's really important. And because the action is invariant under this Weyl symmetry, you get to reduce this infinite dimensional space down to a much more manageable space, because you can also gauge that symmetry. So it's sufficient to only integrate over metrics on your surface and mod out by diffeomorphisms and Weyl transformations. And because you're getting this extra symmetry, it actually turns out that the space that you're integrating over here is finite dimensional. So this is a finite dimensional space. And it's very much analogous to the space of all these Schwinger parameters. So they correspond to Schwinger parameters. This space, by the way, is it's very famous in math. It's the same as the modular space of Riemann surfaces. You don't need to know what Riemann surfaces are. If you know, that's great. Let me also introduce the notation. This is typically called M, curly M, Gn, and G is the loop order, also called the genus of the surface, and N is the number of external legs. So what you should take away from this is that every quantity in string theory, or let's say string amplitudes, they will be presented as integrals over this space. Okay. Any questions so far?
When you're modding out the diffeomorphism times a vial, is that the same thing as integrating out the gauge group in like the Faddeev-Popper setting when you have non-abelian gauge fields?
It is exactly the same technique that you're using, yes. So you're going, to actually do the integral, you will need to introduce ghosts for this gauge symmetry. And those ghosts, so there are these usual Faddeev-Popov ghosts. And once you gauge fix your theory, meaning that you pick some specific representative of a metric modulo diffeomorphisms and vials, then you have your original worldsheet action, which was essentially the area of the worldsheet. But now you're also going to have ghosts that arise from this gauge fixing.
Oh, okay. Thank you.
Yeah. Very good.
Sorry, that's a very out there question, but what's so special about turning it into a line, turning our particles into lines instead of, say, turning them into particle sheets?
Very good question. Excellent question. So this has a very long answer, but I'll try to give you a sort of short answer. Okay, so there's kind of two answers to this, I think. So people have tried, of course. And so what happens is what happens essentially is that there's a technical problem. The technical problem is that we do not know how to do this quantization because so you can try to do the same thing and you will integrate over metrics on your whatever higher dimensional thing you want to replace it by, modular diffeomorphisms. So then this miracle here, this does not happen. So you might not be very impressed by this miracle, but this miracle really only happens for strings. And only for strings you can get still finite dimensional integrals. So for higher dimensional cases, you just need to integrate over all metrics on some 3-manifold, and that's essentially an intractable problem. And in fact, it has been shown that these integrals typically are not very convergent, and it's kind of a mess. So that's one answer, that there's a technical roadblock that nobody has been able to clear. There is also a more conceptual answer, is that it turns out that so in string theory you're starting we're doing perturbative strings because we're basically basing everything on perturbative QFT. And so there's a small parameter in the game that I haven't really told you what the small parameter is, but it's completely analogous to what you have in QFT. It turns out that these are not all objects in string theory. There are also non-perturbative objects in string theory. And these non-perturbative objects actually do include higher dimensional things. So these higher dimensional things are often called D-branes. So these are objects that can have any dimensionality, not just strings. And so they are already part of the theory, but they are non-perturbative objects. So you cannot find a perturbative starting point to quantize them in this way. And there are even dualities that exchange these other objects with the fundamental strings and so on. So they're, in some sense, they're on the same footing as the fundamental strings, but they're non-perturbative, so they're extremely difficult to access. It's a bit similar to the QCD string, I would say. And you can base the QCD string as a perturbative theory based on quarks and gluons, but you can also try to base it as a theory on you can try to treat the QCD string as your fundamental degree of freedom in the theory. And what you do in some sense is up to you, but if you want a perturbative starting point in string theory, you have to start with the strings. But in some sense, string theory is a misnomer because it's not just a theory of strings. It's a theory of all kinds of dimensions.
Just another out of nowhere question. In QFT, you get non-point like objects in effective theories, right? I mean, go all the way down to I don't know, square whatever.
Yeah.
Should I think of D-branes in a similar way as as something you could capture in an effective version? And then, right, I mean, there's some power counting that you need to think of in terms of scales and whatnot. Is there a
In
power?
principle, yes. Yeah, in principle, yes. I mean, these are dynamical objects, so they will have some tension and blah blah blah. But you can include them in low energy effective actions. So you have the low energy effective action of sort of the closed string sector that leads to gravity, but then these D-branes and so on, they come from open string sectors and they couple to gravity, and you can incorporate them in the low energy effective action, and you can try to quantize that again and so on. Yeah, it's all the same essentially as in the cases you're mentioning.
All the same, of course, with a number of caveats here and there, I'm guessing.
Yeah, I mean, here the only thing is that you can actually quantize this object exactly, the fundamental string, whereas usually with just treating it as an effective field theory. Very good. Great. So then I'm going to just make a bunch of comments now. So there are some technical things under the hood that I don't want to get into too much, but let me tell you some of the things that are going on. So I told you an important thing, even though it sounds kind of technical, is this Weyl symmetry. And the Weyl symmetry is kind of a dangerous symmetry because Weyl symmetry rescales the metric, which means that it changes length scales on the worldsheet, which means that it mixes IR and UV on the worldsheet because if you, for example, take phi to be constant here, you get to essentially zoom into the worldsheet. So we also say the worldsheet theory is a conformal field theory because it's independent of the scale in which you're looking at it. And in QFT, that's a dangerous thing because typically if you go to the quantum level, you develop scales, even though your classical theory might not have had a scale. So even though classically your worldsheet theory might be invariant under this Weyl symmetry, typically this is broken at the quantum level because you're computing beta functions, and the beta functions will make it not invariant under Weyl symmetry. Another way of saying this, if you treat your 2D worldsheet theory as some QFT, you have to put some regulator in, and these regulators will always break this symmetry. So you have to be very, if your quantum theory preserves it. And so let me write this. So the Weyl symmetry is in general anomalous. Anomalous just means it's a symmetry of the classical theory, but it's broken at the quantum level. And so there is a condition that for this whole thing to be consistent is that all the anomalies cancel. So anomaly cancellation requires two things, essentially. So it requires that the dimension of the target space is exactly 10. That's the first thing. And the second thing is that the target space on which your string is propagating, we usually call it target space, but it's just a background manifold on which you're putting the string. The background manifold satisfies Einstein's equation. So far we have put it essentially on a flat space, so you can scatter strings on flat space, but there's nothing that prevents you from scattering strings in a black hole background or whatever kind of background you want. But there's a condition: not every background will work, only those that satisfy Einstein field equations work. And in principle, so it's to be completely honest, it's Einstein's field equation. There's a bunch of additional fields that appear, so it's really supergravity, equation of motion. And there you can also compute quantum corrections to this. So this is the leading order. At leading order and weak curvature, you get Einstein equation, but then there are successive corrections to that correspond to the higher loop beta functions on the worldsheet. This dimension 10, so this is space-time dimensions. There's various slightly different versions. So the one that I told you about now is maybe. So this is for the superstring. You get 26. You get 10 dimensions, where there's also a bunch of fermions around in the construction that I haven't talked about. If you just take bosons, you get 26 dimensions. But the bosonic string is clearly not the one that describes nature, because it does not have any fermions and it has other problems. So you should essentially ignore this 26. So that's the sort of the very bad news that you might have heard about, that string theory only works in this high dimensional backgrounds. And then we go back to the problem that we described in the motivation, is how do we connect with lower energy physics? Well, you're going to have to make some choice for this background manifold. And your choice is going to be something like R13 for our real world dimensions, and then times Calabi-Yau threefold or something like that. So that's some specific 6-dimensional manifold that satisfies Einstein's field equations. Very good. So that's
so you say now you've chosen a certain manifold that satisfies this d equals 10, but so are you able to distinguish between like temporal and spatial dimensions? You said you have 10 space-time dimensions. How do you quantify whether it's temporal or spatial?
Yeah, it's one temporal and 9 spatial dimensions.
Okay, right.
So I think it's really weird as a concept if you have more time directions.
Yeah. So string theory is not consistent with more time directions.
But is this a choice that of a type that you can deal with, or is there really a no-go theorem that you cannot do anything else? As in,
you mean more temporal?
Yeah, right. More temporal directions.
Well, the theory will not be unitary.
Squeeze away in a weird way.
So yeah, the theory will not be unitary. So what technically you're doing is you're proving that you start with some theory. This original worldsheet theory is not going to be unitary theory because there's a temporal direction. Yeah. So it's just like what you do in QED. That there are some oscillators in the time directions that lead to negative norm states. And then after quantization and imposing gauge constraints, you want that the reduced Hilbert space is unitary. And essentially, the gauge degrees of freedom in QED, say, are exactly enough to remove the temporal oscillators. And you remain with 2 polarizations, and they're transverse polarizations. And those polarizations are unitary. The same happens in string theory, that basically the amount of gauge symmetry that you have, which are these diffeomorphisms and bisymmetries, are exactly enough to remove the temporal oscillator degrees of freedom, and you remain with transverse oscillators. And those transverse oscillators lead to unitary states. But if you're going to introduce more time directions, you won't have enough gauge degrees of freedom to remove all the negative norm states. So in that sense, it's not consistent. Very good. But in the following, I will just take this background manifold to be R1, 9, essentially. So I'm just going to talk about flat space, 10-dimensional things. Good. Then the second important comment is that all these amplitudes are UV finite. And the reason is essentially that in field theory, if we go a little bit back up, so in field theory we had this we had the problem at large momenta. And large momenta, after doing this transformation, corresponds get mapped to short distances here. Because if I make momentum very large, then this integral is going to be dominated at very short lengths. And you can see that this integral is divergent now from very short lengths, essentially because of this divergence here. And so the dangerous part is short lengths. So if your worldsheet is becoming very sort of chubby, but you can see because, so in field theory, you can make very short loops, let's say, and this is where the divergence is coming from. Whereas in string theory, you can't really do that because if you're making your, if you're trying to make your propagators very short in one direction, well, there's a second direction, which is the direction of the spatial direction of the string in which it's still long. And so you cannot make it short in all directions. Sort of the intuitive way of saying it, the more rigorous way is if you study this space MGN, then MGN just does not contain any region where propagators become short. So MGN excludes regions with short propagators. Maybe that wasn't very understandable, so let me try it once more. So if you, let's say you want to compute a one loop partition function, so you're just going to have a torus. But now again, the dangerous region in the torus, which would correspond to some determinant in QFT language, if you make one cycle of the torus very short, and you think about this, the torus, let's say, as a square where you identify opposite sides. If you make one cycle very short, it's going to look something like this. And then you might be worried about this very short propagator here. But the point is you could just flip the torus. And if you just draw it in this direction, well, now you see that you, even though this propagator looks very short, it's actually an IR singularity because there's another propagator that becomes very, very long in the other direction. And so there's never any place in modular space where both cycles become short, because both cycles becoming short, you can remove it by just, so the scale of the square or the rectangle is not meaningful because you have this Weyl symmetry. So if you try to make both propagators simultaneously short, that's just part of this Weyl action that you anyway modded out. So this phenomenon often goes under the name of modular invariance. And so how string theory cures UV divergences is really in sort of a dumb way because it never integrates over the relevant regions of your worldsheet. Good, hopefully that's roughly clear. Then another comment I want to make is that there is only a single diagram at every loop order. So in field theory, typically you get many, many diagrams. If you're trying to compute a 10 loop process, you get like roughly 10 factorially many diagrams. Whereas in string theory, there's just one diagram per loop order. So in some sense, it's much more economical than field theory. The price to pay is that this one diagram is going to be very hard to compute. Another comment is that the string has in principle many vibrations. And all these vibrations correspond to different particles. So in particular, you have the tachyon, you have graviton, you have fermions, and so you have in particular massless particles, and you have also massive particles. So the massless particles include gravity, but then there are also various fermions and other fields around. And then you get a bunch of massive fields. In principle, when you do these amplitudes computation, well, you have to make a choice for what your sort of external particle is that is coming in here. So you might want to scatter gravitons, you might want to scatter other particles, and that information is given by specifying some asymptotics of your worldsheet as it goes out to infinity.
So you said that different vibrational modes correspond to different types of particles, and they can be either massless or massive. But
Right.
how do you what types of vibrational modes correspond to massive or massless particles?
Essentially, the ground, sorry, what's it called? The base frequency of the string corresponds to the massless fields. And it can vibrate in different, also it's embedded in target space, so it can vibrate in different directions. And then there are all the sort of higher harmonics on the string. So technically you're doing some Fourier expansion on the string, and the constant mode will be the massless particles, and then you have the higher modes, and they correspond to more massive particles.
Okay.
In string theory, you have particles, and they have mass, let's say mn squared, and that mass is something like some number times n, where n is a positive integer that essentially corresponds to this Fourier mode.
Yeah.
And then there's some scale here that I introduced. This is the string scale. So there's one scale that you have to introduce in this whole game, which is the characteristic length scale of the string, and it's dimension full. And it appears again in the mass here. So this alpha prime is essentially the string length, the characteristic string length squared. And the 4 is just conventions. Very good. All right, so I think I'm essentially out of time, but if I may, I want to take essentially 2 more minutes and give you an example.
Also take 10 more minutes if you need it. Just explain it well.
Okay. Very good. So then, so far I just made sort of random abstract comments, maybe. So I just want to show you that it's actually a theory in which you can compute things. So let's discuss now the leading term in this expansion. So let's discuss the tree-level diagram. So that is the diagram corresponding to scattering of, let's say, gravitons, but without the loop in it, because that's much harder. Well, then this is going to be an integral over, let's keep some space here, over the space M04. So it's the space of metrics on this surface, modulo Y transformations and diffeomorphisms. And this space is actually a 2-dimensional space, this M04. And it's sort of easy to understand what the 2 parameters are. So if we go back to field theory, then we have this exchange diagram in phi cube theory. And there's there's one parameter, which is the proper length along this segment. In a string, this gets lifted to 2 parameters because essentially one parameter tells you how the proper length is of this piece. And the other one tells you if you take the 2 components of the surface, then you can twist them along each other, because so you can specify essentially an angle between the 2 parts of the surface. So often we say it's a length and a twist parameter. And so the length is directly translating into the length that you have in field theory. And what's nice is if you look at the space, actually it matches together to one complex variable. So it becomes one complex variable, and you can take this complex variable to run over the complex plane. And if you want to make connection back to this, I'm going to tell you in a second. And then there's some explicit integrand, and the integrand is actually pretty easy. It's something like this. So the integrand has three singularities, namely when z hits, let me exclude 0, 1, and also when z goes to infinity. And those three singularities correspond to where two of these external operators collide, essentially. Or another way to think about it is you have exchange diagrams, and there are three possible exchange diagrams in the QFT. You have this, and you have, sorry, last one's always difficult. You have this one. So there are three possible ways these operators can collide, and three possible ways in which the surface can develop some very long tube. So in the string way of thinking about it, you should think of the first one as being a four-punctured sphere that looks something like this, with a very long propagator in between. But this propagator can also become long in this direction, or it can become long in this cross direction. And those three special points in moduli space, on the space of surfaces, correspond exactly when this z parameter here goes to 0, 1, or infinity. Let's say it goes to 0, corresponding to this scenario, then this z will be something like e to the minus l, so making contact with this proper length, plus I times the angle. And then I should remove the absolute value. Okay, so that's how this parameter connects with previous parameters. Then, of course, this is, so I haven't told you which external states we want to pick. Sorry. Let's pick the gravitons as external states here, so that we're computing gravity amplitude. And then, of course, there will be various polarizations around, because a graviton is a spin 2 field, and will have polarization tensors of the form epsilon mu nu. And so there will be four polarizations, and the four polarizations have to be contracted somehow. And so typically, this is denoted by some polarization tensor, and this polarization tensor has some name. People typically just call it T8, T tilde 8. I'm not going to write it out, but it's some contraction between all these four different polarizations. So this is the polarization tensor. But it's the same polarization tensor that appears if you compute, say, the tree-level Feynman diagrams in GR. You will also find some polarization tensor, and it's the same one. And so the interesting thing about string theory is essentially this integral here. So it gives you some integral that is the scattering amplitude, and you can actually evaluate this integral. So let me tell you what the answer is. It's a bunch of gamma functions. So here S, T, and U are the Mandelstam variables of the scattering process. So S is something like P1 plus P2 squared, and T is something like P1 plus P4 squared, and U is P1 plus P3 squared. Okay, so again, there's there are many miracles that happened. One miracle is that first of all, there's a single formula, which is already surprising, because if you do field theory, you would think that there's a sum of different terms that you need to add up. So these three plus the contact diagram to get to some final formula. And typically you will not get it's very surprising that you get this factorized form. So in particular, you see that this is manifestly crossing symmetric. It also has the property that people call dual resonance. So in the old day, string theory was called dual resonance models. The reason is that because these gamma functions have a bunch of poles in them. And in fact, they have precisely poles whenever S hits one of the masses of the theory. So I wrote down the masses above. So whenever S is of exactly this form, you will get a pole in the amplitude, which means that one of the internal propagators goes on shell. And you see that you only have to put in, say, the poles on the S channel. And if you sum over all the poles, you automatically get the poles in the T and the U channel. So in some sense, you only have to put in, so if you would describe it from effective field theory point of view, you would only need to sum over one type of diagram, And if you resum over all possible particles, you also find all the other resonances in it. So that's where the name dual resonance comes from. Another surprising property is, well, let me first make a not surprising property, is that this whole thing is unitary. It's consistent with partial wave unitarity, which means that if you decompose this into partial waves, all the coefficients of the partial waves will be positive. So that's, again, goes back to this 2 time directions and so on. If you do things like that, you will generally break unitarity. But maybe now the most interesting property is that the whole thing is UV soft. So if you look at scattering amplitudes in QFT, then again, this will be something like roughly 1 over S plus 1 over T plus 1 over U plus a contact term. So if you go to very high energies, this is essentially approaching constant in QFT. Whereas if you do string theory, it goes like, so if you go to very high energies, which means that you're taking S and T very large and you're fixing the ratio, which is related to the scattering angle, this whole thing decays like exponential of S times some function of the scattering angle. And there's also alpha prime here. So the amplitude exponentially decays in high energy limit. And that's quite surprising that the cross-section goes down exponentially fast. That's what happens at tree level. And then, of course, the question is what happens for the non-perturbative amplitude. So this is really at the heart of these questions that we want to probe, because we want to take the amplitude and go to very high energies and see what happens to the theory. Good. I should also mention this is the Virasoro-Shapiro amplitude, and it has kind of a curious history because it was found before the string theory was developed. So because it has all these nice properties, and they sound like nice properties, but they're actually incredibly constraining. So if you just try to write down an amplitude, which is some function of S and T, that has the correct properties in the sense that it has poles corresponding to massive particles in the theory, it's unitary, it's crossing symmetric, all these kind of things. It's actually very, very hard to write down these amplitudes. And Veneziano and later Virasoro-Shapiro came up with this answer that this is essentially the only function they could think of that has all these properties. And it turned out that string theory is actually a theory that computes exactly this function. So that's quite amazing, I think. That just also goes to show you that you cannot do whatever you want in the UV. It's very, very constrained. There are many constraining properties that, yeah, you cannot just do whatever you want. Okay, I think I'm going to stop here since I already went over time, but I'm happy to have more questions.
One's left. So are there any questions in the room at this stage? Yeah.
Maybe just one, because I missed it. Are we here computing the amplitude or the squared amplitude?
The amplitude.
Okay, just the amplitude. Okay.
Yes.
Okay. Yeah, I had to think about it.
So I'm just curious. So you say that the amplitude here, it's a surprising result that it decays with this e to the f of theta.
Yeah.
What is the real physical interpretation of that, if there is one, in your mind?
Yeah, so if you go to high energies, essentially you're so there are many attempts, but one is essentially that I like is that if you go to high energies, the string becomes large compared to the interaction cross section. And essentially you should think of like the particles are as small as you want, so you can always let them interact at high energies, but somehow the string, because it's extended and it runs through the other string at very high energy, it sort of can only interact at a very small portion of the string. And it cannot interact over the whole string. And that's roughly why why the cross section is supposed to go down.
Thank you.
Any more questions in the room?
Well, if you're just back to the Planck scale, right? You tie yourself to a base manifold that has some Einstein maybe plus stuff geometry on it, and that brings the scale by itself. Is that the link? Right. How do you know about the Planck scale? This is what
Very good. Yeah. So you know about Planck scale. So I introduced this kind of arbitrary scale that I call alpha prime.
Okay.
But it's related to Planck scale. So I haven't really talked. So there's also a coupling constant in the game that I haven't talked too much about, which is just the analog of the coupling constant in phi to the 4 theory. And it basically weighs different worldsheets according to the loop order. So you have one dimensionless constant in the game, which is this coupling constant. Let's call it G. It's usually called G string. And this would go like G string squared. Sorry, that would go like G string to the 4. And so it's a combination of this dimensionful constant alpha prime and G string that becomes the Planck scale. If you want to work out the relation, so let me also put the correct G string factors here. Then I need to put G string squared here. Well, you just need to compare this to what you would compute in gravity. In gravity, you would compute some diagrams like this, and you would take the Einstein-Hilbert action, and you would expand it around flat space. And then the cubic coupling, because the Einstein-Hilbert action has a 1 over g Newton in front, right? So if you expand around flat space, the cubic coupling will go like square root of g Newton, and there will be another square root of g Newton over here. And so now you can relate g Newton, which is in turn essentially the Planck length. You can relate it to this g string as well as alpha prime. And the relation that you find is that g string is related to 1 over square root of g Newton. And then you have to put the correct power of alpha prime. I keep forgetting it's something like dimension minus 2 over 2 or something like that. So to make this whole thing dimensionless. And then you can solve what the Planck scale is. So the result is that if you're at weak string coupling, then the Planck scale is much higher than the string scale. If you are at, so meaning this G string is small. If you are at strong, or if this G string becomes of order 1, then the string scale and the Planck scale are at the same order.
Good. Thank you.
All right. Are there also any questions online? I guess it's just Jared left. No?
No.
All right. Well, then let's thank the speaker one last time.
Thank you.
Thank you for giving this very nice talk, Lorenz.
Yeah, hopefully I was able to